Today I'd just like to give you a brief introduction and overview of 1801 UPF. In the 30 minutes we have, I can't really go into too much details, but I'd like to give you a bit of an insight to the methodologies and concepts behind UPF, before then going on to talk about successive refinement in something that is of particular interest to us as IP providers. And then I'll wrap up with a little roadmap of where we hope to go over the next couple of years. So what is UPF? It stands for Unified Power Format, and it basically describes the power intent that you don't have in your design languages such as Verilog and VHDL. It's based upon Tickle. You can mix it with regular Tickle, so you can build up more complicated structures. And you use it for both verification and implementation. It's an evolving standard. We started on this in about 2006, and it came out under Accelera first in 2007. That's known as UPF 1.0. Then it was donated to the IEEE, and in 2009 we came out with the first IEEE release of UPF, and just last month, actually, no, it's 1st of July now, isn't it? The end of May, we had the 2013 version of the standard. So the main components of UPF, really the principal component is a power domain, and the power domain is a collection of elements that all share the same power supply requirements. And then with these power domains, you need to distribute the power to those domains through your supply network, which consists of ports, nets, supply sets, switches, etc. And then perhaps the next most important thing in UPF is the power state table, which describes the legal power states of the power domains in your design and the legal transitions between those power states, and implicitly, I guess, the illegal ones too. You also have isolation strategies, which describe what you should do with ports on a power domain should the primary power be removed. You also have retention strategies that say what state in the power domain needs to be retained through power shutdown. And if you're running on multiple supplies, you may have level shifter strategies too. And new for 2013, we now have repeater strategies which describe how signals that pass through power domains should be buffered. So taking power domains first, I just thought I'd run through some of the principal aspects of UPF with a few very simple examples. So if we set our scope at the top here to this logic structure, the subsystem, that's what sub stands for, and we create a power domain, PD sub, and say include scope. So basically everything from sub down gets put into that power domain. And then if we create another power domain, we call it PD proc, and we say the elements are P1, then we call out of the previous power domain those elements that are part of this power domain. So this is the form of where the more specific command overrides the more generic command. And so we can do this again and pull out the memories and create a power domain for the memories here as well. And similarly for the second processor we can do this too. One thing important to note is that all of the names, the power domains, were created in the scope sub. So even though we've created what looked like a hierarchy of power domains, they are in fact all flat at the top level because that's where we created them. We could have moved through the hierarchy as we were creating them if we wanted to. So supply sets. Supply sets is something that's new in the 1801 standard. These didn't exist in UPF 1.0. Supply set is a collection of conductors that represent a complete power model for your supply set. So you've got power, ground, N-well, P-well, and perhaps deep N-well and deep P-well, depending on your target process. There are some predefined supply sets for each power domain. There is primary power, retention power, and isolation power. And the nice thing about these supply sets is you can refer to them by a handle. So you can refer to them as such and such a power domain dot primary, .default retention or .default isolation. And this allows you to talk about the power supplies to a power domain in an abstract way and not have to get your hands dirty with the actual implementation specific names of the individual supply functions. The other thing that you can use the supply set names for is when you're creating strategies, you can filter on the supply set names. So you could, for example, with isolation, say I only want to isolate the ports that are driven by PD.primary or sunk in PD2.primary. So you can use that for filtering the ports that the strategies apply to. So each one of these supply sets has a concept of a sim state, and the sim state is basically telling you what the simulation semantics are for that state of the supply functions in the supply set. And the two normal ones are when your supply set's corrupted and when your supply set's normal. However, more interestingly, you can have things like corrupt on activity. So this is the state of the domain will remain true unless any of the inputs change. Or you could refine that further and you can have corrupt on change. This is similar to corrupt on activity, but the outputs have to change this time. And then you could even be a little bit more conservative and only look at the state rather than the combinatorial logic for seeing if its outputs change. And then one sim state that was missing in the 2009 version of the standard we just added into 2013 just to make it all symmetrical is corrupt on state activity. And there down at the bottom is a little code fragment of what it would look like when you add sim states. So here I've got sim state normal for run, sim state corrupt for off, but I've got sim state corrupt on activity for my drowsy state, which means in drowsy it will maintain state unless I do some any inputs change. Also in 2009, 1801, we've introduced the concept of power state as opposed to power state tables. It's a much more sophisticated and complex command, and it allows you to attribute both power state to supply sets and domains. So here I'm attributing some power state to the domain PD memory, and I'm saying it's in run when the primary supply is at 0.8 volts. And I'm saying it's in state off when the primary supply is off. And then I go ahead and build my power state PD proc, and I build that in terms of the state of the memory domain and also the state of the supplies to PD proc. So just looking at the first one there, you can see it says we're in state normal when the primary is at 1 volt, state on underscore 1.0, and the memories are on 0.8, but the memory is in state run. So this allows you to build hierarchical state tables, something you couldn't do in UPF 1.0. It's a very powerful feature. Power switches. In order to implement your various different shutdown domains, you can describe your power switches. Now, in order to simulate your UPF, you don't actually have to have a power switch. You can do it, as we were on the previous slide, with logic functions, but you may choose to actually put in a switch that implements the logic function. And here I'm showing a switch, and you'll see, I haven't got a pointer, I'm afraid, with the virtual presentation, but the first port name in the list between the curly brackets is the name of the port on the switch, and the second name in the curly brackets is the name of the net in your design it connects to. And this is a logical switch which may be implemented by many physical switches. Isolation strategies. Here's just a very simple isolation strategy I've defined for this power domain. And I've said I want the isolation strategy to apply to all outputs, clamp value 0, and it's asserted when my isolation signal MISO goes low, and the location self. So the isolation switches are isolation cells are put into the proc power domain. That's what isolation self means. We also have, location self means. We also have other locations like parent and other. other is a generalized version of parent. This is something that is also new for 1801-2009. When you have a power domain and you call out another power domain from within it, perhaps somewhat counterintuitively, there is an upper boundary to your power domain and there's also a lower boundary. And if you use location parent on the lower boundary, because it's relative to the logic hierarchy, you might get your cells not where you expected them to be. So you need to use location other. Location other means basically just put them outside my front door and back door. So up one level of hierarchy at the top and down one level of hierarchy at the bottom. Level shifting strategies, similar to the way you define isolation strategies. Again, here I'm just saying applies to all outputs, location self, and I'm putting in a level shifter that is going to shift the logic level from 0.8 volts to 1.0 volts, going from the memory up to the processor. And each one of these strategy commands has the isolation and level shifting commands have this use interface cell command. So if the EDA tools are unable to infer the correct cell out of your technology-specific library, or you particularly want to use a certain cell, you have that under your control. You can say use this cell, and that gives a directive to the tools to use a technology-specific cell. There are also retention strategies. So if you shut down a power domain, you may choose to retain certain state. And with the retention strategy here, I'm retaining all the state, and I've got a two-signal strategy. I've got a save signal and a restore signal. There's also support for having a single control to your retention, and there's also now new for 2013 support for live slave retention, as well as your traditional balloon flop style retention. So that was a very quick overview of the components that are in UPF. I'd now like to talk a little bit about some of the concepts of using successive refinement in UPF. This is a feature that was introduced in 1801-2009 and has been more thoroughly described in some informative annexes in the 2013 standard. So an IP provider would provide some RTL here. On the left-hand side of my diagram, we have IP creation. And the IP provider would provide some constraint UPF. So this constraint UPF describes the inherent low-power intent that's part of the IP. And it's the things that, as a licensee, you need to obey when configuring the IP. So this would be what an IP provider would deliver to the licensee. The licensee would take that RTL and UPF and configure it for their application-specific application. And they would add to that some configuration UPF. And then that would essentially become the golden source, the point of reference against which the technology-specific physical implementation would be compared against. So we hand over now the RTL, constraint UPF, and configuration UPF essentially as read-only files. That's what those little padlocks are trying to show. And then add to that some technology-specific implementation UPF. And then you have your implementation flow as normal indicated at the right-hand side of this diagram. And at any point down that flow, you can take your HDL, be it at the Verilog or VHDL level or netlist level, together with the UPF, and they should be functionally equivalent. So you should be able to simulate at the RTL plus UPF level and at the netlist level, or perform LEC between them, and they should all be the same. So just to recap, a soft IP provider really only need to declare these four things. They are simply the atomic power domains in the design, and they're the power domains that can be merged but not split during implementation. And then for each power domain, you need to declare what state must be retained during shutdown without prescribing how the retention is controlled. the signals on the power domains that need to be isolated, high or low, without prescribing exactly how the isolation is controlled. And then, perhaps most importantly, the legal power states and the sequencing between them, without having to get involved with supply net names or indeed voltage values. So once an IP provider has provided those things, the licensee can configure within those constraints. Now, this is all a little bit abstract, and I thought it might be brought to life if I just run through an example. So in the short time we have available today, I'm unable to go through my hierarchical example. I normally do an example that involves a 4 CPU ARM core, such as Cortex-A7 or Cortex-A15. So what I've done is I've just taken out the CPU, and we'll just do the CPU rather than the full hierarchical one. So in terms of the constraints, what we as an IP provider might hand over is simply where these atomic power domains are. Now, in my very simple example, I've got a CPU with an FPU subdomain. So what I'm going to do here in step 1 is create a power domain PDCPU with elements dot. So I'm basically putting everything into that domain, but specifically excluding the FPU. And then I'm creating a power domain with the FPU. Now, the reason I had to specifically exclude it is I put this switch, which is new for 2013, dash atomic, and that makes this power domain indivisible. So now as an IP provider, we've declared that power domain, it has to stay. And now I'm saying in step 2 here, the retention requirements are basically, I create a retention list here, set retention elements, would put every element into it. And the semantics of retention element list is everything in that list must be treated in the same way with respect to retention. So you either have to retain all state or no state. So that's a way of us ensuring that people don't attempt to do selective retention on one of the ARM processors. And then the isolation requirements here, I'm using set port attributes, and I'm saying that I want to clamp everything low except for 1 or 2 ports that I want to clamp high. So again here I'm exploiting the successive refinement and putting in the more detail overrides the more generic. That's what I'm trying to say. Oh, I forgot my builds. I'm sorry about that. I'll try and remember it on the next slide. So a second slide of constraints, this will be the power state of the CPU. So I begin here by building the power state of the FPU and defining it in terms of its supply sets. So the FPU has got a primary supply set and the retention supply set, and I'm just defining these 3 states, run, retention, and off, based on the states of the supply sets to the FPU. And once I've done that, I can then go ahead and define the CPU in terms of its supply sets, but also the state of the FPU domain. So I'm saying when the primary is on, and the retention is on, and the FPU is on, we're in state run, etc. Okay, so just referring back to that successive refinement diagram, we're now at the point where these are the constraints that would be handed over to someone who wants to configure the IP for their application. So just before I move on and talk about configuring the constraints, I just wanted to touch very quickly on hierarchical versus flat. With flat configuration, you can configure everything from the top level. You have full visibility. It's like white box, and so you can kind of reach into the blocks below and refer to port names, instances, and do all of your configuration from the top. So I could create an isolation strategy in all of my power switches and refer to the switch controls. You know, I'm sitting at the top level. I can refer to the output of my power management unit for the isolation controls, the power management controls, and I can put the switches and isolation into my design. That's very nice and easy and straightforward. However, quite often people want to do a hierarchical flow for capacity management or concurrent engineering reasons. So in that case, you have to configure your IP out of context, and it's a little bit more complicated. And you need to use these new commands that were put into 1801-2009 that weren't there in Accelera 1.0 to create logic ports and nets and then you can wire up your switches and isolation, etc. to those logic ports and nets. Then you instance your hard macros into the next level up, and then you would configure the next level up with the ports that you require and connect those through, and so on, all the way up to your power management unit. And whilst we're briefly just talking about tips and the relative merits of hierarchical versus flat, I'd also just like to touch on so-called redundant isolation between power domains. When you have a multi-element power domain, it can lead to unexpected intra-domain isolation. What I mean by that is, if you imagine you've got a block here, top with 3 sub-blocks A, B, and C, and you create a power domain red out of A and B, you may be surprised and disappointed to find if you shut down power domain red, you will get isolation on any net that leaves A and enters B, even if it goes nowhere else. And this is because if you stop to think about where that wire is, it's defined in top from a Verilog point of view. And so technically it doesn't belong to PD red. That is why you get the isolation between those domains. It's just a common gotcha I wanted to highlight. You can avoid this by taking a different approach. If we were to create PD red at the top level, put everything in it, and then call out block C and put it in PD blue, we now have PD red including top, so you won't get that problem. But unfortunately, that's not always possible if you have a more complicated power domain hierarchy like this. So my advice would be, if you can, please try and align your power domains with your logic hierarchy, and it makes this problem go away. Failing that, you can use a new command that we introduced into 2009 called diff supply only, or indeed the more powerful source and sink filters to more accurately describe your isolation strategies. So back to our little example. In order to configure the constraints that I outlined, I'm going to choose here to merge the FPU and CPU domains together. I've decided it's not interesting to have a separately switchable FPU domain, so I'm going to use the command create composite domain, and I'm going to create my PD CPU and put in the FPU and CPU into that domain. And then I'm creating the control ports as we described. I forgot to mention I'm doing a block hierarchical bottom-up implementation. So I'm having to create those control ports, and then I'm having to create the isolation strategies to fulfill the isolation requirements, the attributes I put on the ports that said that it must be clamped high or clamped low. Oh, I forgot my builds again. Sorry about that. And then with the CPU configuration on the state side of it, we're now going to update the supply state with supply expressions to give a bit more detail of what it means when we're on and off. So we're now saying to be on, power has to be full on, ground has to be full on, and we're off if either of them is turned off. And I'm going to decide that in the CPU, I'm not interested in retention either. So I'm now going to use the update command to add power state. So I'm going to add some more detail. So even though constraints that run retention and off are all valid power states, I'm now declaring retention to be an illegal power state in my configuration. And I'm also updating the power state for the FPU to show that it's only on when the power control signal to the CPU is on. So the N power up CPU is controlling the FPU power domain as well. And finally, because I created a new power domain, that composite power domain that was based on the FPU and CPU, I just need to describe the state for that, and I'm going to describe it in terms of its constituent CPU and FPU. So we're now at the point where we have a fully configured implementation independent golden reference ready for implementation. The reason I wanted to go through this in such detail was I think it's very valuable with IEEE 1801 to be able to create this technology independent golden reference so you can invest lots of time and effort in your verification and validation of this independent of its subsequent technology specific implementation. Previously, in order to have a simulatable RTL plus UPF, you would have had to got your hands dirty with naming power supplies, physical switches, all sorts of things that once you've done your validation, if in the target technology those names and configuration changed, it might lead you to think, do I really need to go and repeat all my validation? And the answer is probably yes. So this allows you to preserve the investment you've made in your verification equity. I won't go through this slide. It's just finishing off the configuration, constraint configuration implementation. It's more for the physical implementation guys. So finally, you now have an implemented block, and you can hand that off as a hard macro up to the next level. And with a hard macro, there's no need to re-verify the low-power implementation. You just need to verify its integration. And in order to do that, you need to have a power-aware simulation model that has the correct corruption and retention behaviors. You need to have assertion checks on the I/O to check for the correct sequencing of power controls, etc. Now, most of this can be done within a Liberty model that has power and ground syntax. That was something that came in a couple of years ago. Or you could create macro-level UPF that is more descriptive than directive. Again, I think in the interest of time, I'll skip over some of the details there. So that's a quick whiz through of UPF. I then wanted to just talk about the work group very briefly. The P1801 work group is an entity-based work group running under the auspices of the IEEE Standards Association. And we currently have 18 entities actively involved. We usually get about 20 to 25 individuals from these 18 different entities at our meetings. As I was mentioning at the beginning, we've just released a new version of the standard. Why did we do that? The motivation was, of course, to address the known issues that had been identified in the 2009 standard, but we also wanted to go and improve the clarity and consistency with which the standard was written. So we added some clarifications to do with precedence ordering, to do with the lower boundary of power domains, things like that. We also added some restrictions. We removed some of the UPF 1.0 type accelera commands, and we made some additions of notably the set retention strategy and also the ability to declare equivalence between supply sets. But along all the way, we also included a limited number of critical enhancements, and in particular worthy of note was the improved support for macrocell modeling, which I was just referring to on the previous slide, and also the ability to attribute pins and cells in the library with low power metadata. Now, this last two things principally came from contributions from SI2 CPF. Cadence made some contributions, and SI2 wound up giving us access to the entire CPF 2.0 specification. And as a result, we managed to achieve an improved convergence in methodology between UPF and CPF in the 2013 standard, which is very good news. In redoing the 2013 standard, we revisited each and every command, and in particular we rewrote the major commands, set isolation, set level shifter, set retention, and made them have a more familiar feel in the way that they are all written in described in a similar way. But we also completely rewrote the sections on UPF concepts, language basics, and simulation semantics, and added new sections. In particular, one that I think is worth looking at is these informative annotations I was referring to before. Annex E is on low power design methodology. In previous versions of the standard, the IEEE would not allow us to put informative information into the standard. It all had to be normative. Those rules appear to have been relaxed. So the 2013 version of the standard, it's worth checking out these informative annotations. So the 14th iteration of the draft was approved back in March, and we then went through production publishing, and May the 30th it was published. And the good news is, thanks to Accelera, who have sponsored this, you can download it for free of charge from these URLs here. Just Google IEEE find standards, then type in 1801 and you'll get there. This is what the page looks like, and you can see the yellow box there, available at no charge, which is, as I said, great news. 3 more slides, I think, maybe 4. I just thought this slide, a colleague of mine put together, Eric Marshner, who's the vice chair of the work group. It's a very nice summary of how UPF has evolved. So this is kind of what it looked like for UPF 1.0 in 2007. And then in purple, these are the things that were added in the 2009 standard. So you can see supply sets and add power state and things like that were being added. And then here in red is what's been added for 2013. The plans for the work group going forward, we've just had our project authorization request approved by the IEEE Standards Board. So that means we essentially have a charter to work as a formal work group under the IEEE-SA for the next 4 years. And our motivation, of course, again, identifying any known limitations that come to light with the 2013 standard. Hopefully there aren't many. But principally our motivation was to extend the scope of power intent up to the system level. We wanted to add power modeling and estimation capabilities and to take SAFE, which has been languishing in the back of the standard untouched for a few years, and try and integrate that back into the standard. I think it will come into its own now. We also want to consider further UPF and CPF methodology convergence, and then to do some more work on these informative analyses. I was just extolling the virtues of Annex E, but it can definitely be improved. It only runs through 1 or 2 examples. We could build a whole family of examples. So with that, I'll just say, if you're interested in joining the work group, please do let me know. Drop me an email at this address and visit our webpage. With that, thank you very much.
Hang on.
Q&A now.
Yeah, do you want to start in Cambridge? Go on.
Yeah. Got any questions from you? Eamon, come on to the mic. It's easy.
So my question is just, given that some of these new commands that have been added in the more recent releases of the standard support successive refinement, it strikes, but the old syntax is still in there and is still valid. So it strikes me that someone coming to it kind of new could easily go off on a false path if they want to support. So do you have any guide or documentation or anything that kind of lists the syntax that's recommended now for the full successive refinement approach?
Well, just to be clear, successive refinement could be done in the 2009 standard. So that's not new for 2013. That's been there 4 years already. Unfortunately, it's always the case that the flow and capability within that you have access to is limited by the EDA tools you're using. So I think the answer to your question is going to be more limited by whichever EDA vendor you're using, what commands and switches to those commands they actually support. And I think most EDA vendors have a document that describes what they do and don't support, together with a roadmap for plans for future support. Any more?
Sort of a related question. On that, the slide showing the charts of new language features added, that last one was some grey ones.
They're the deprecated ones.
Okay, so
I'm sorry, I should have put that in the key.
Okay, so if you've got UPF for the 2009 version, and you want to run them on a tool set that supports 2013, will that not work on an update?
So our definition of deprecated, which I think is the industry definition, is they're still in the standard.
Right.
They're just not recommended for use. Deprecated means that you're allowed to have them in old code, but you shouldn't be using them in new code.
Are there any tools which are supporting this version?
So the question was, are there any tools supporting this version of the standard? Well, it only got published on May the 30th, which is, what, 5 weeks ago. So I don't know, to be honest. I doubt it. But it depends what you mean by supporting this version of the standard. So all of 2009 is in this version of the standard, because this is building on 2009. So there are, the EDA tools out there at the moment have pretty good support for 2009. So I guess you meant the new features, the bits highlighted in red. I doubt whether the bits in red have been implemented yet. However, I would add, I do get questions from EDA vendors clarifying semantics, so I'm absolutely certain they are working on coding it up right now.
Any more questions from Cambridge? I think we're done here, Sarah.
Thanks, Brian. So we go over to Grenoble. Francois, any questions in Grenoble?
Yeah, apparently there is no question here. Thank you.
Apparently. I guess that means no. Okay, just one question from Bristol. John, it's an interesting talk. I'm just wondering, do you have any statistics yet for the take-up of UPF? Do you know? I know some people do low-power designs but don't use UPF or CPF. Do you have any statistics on the number of companies using UPF?
I don't, I'm afraid. What I could say is it's changing and it's drifting towards, in my opinion, 1801. Cadence have been a very active participant of the 1801 work group over the last probably 18 months to 2 years, and they made those contributions. I could highlight that they made a press announcement not too long ago about their simulator supporting UPF. I believe it's their intention to all their tools will support UPF before too long. But you're asking for statistics today. I'm afraid I don't have that at my fingertips.
Okay. Okay. I think there's no more questions from Bristol. So at that point, hopefully you can hear a round of applause. Thank you very much, John.